Okay, good afternoon, everyone. Thank you for tuning in and or coming to the second Lunch and Learn series. My name is Heather Eastman, and I'll be presenting this next talk to you. So, where are we at? We're at the second session in this 5-session series. Today's talk is going to be some bus and interface analysis. And what we're doing here is we're trying to gauge whether, gauge your interest in whether or not we are going to turn this into a full-blown class, which will go over a survey of non-invasive and invasive techniques for hardware reverse engineering. So your comments and feedback is greatly appreciated. So previously, last week or 2 weeks ago, what we talked about was, the basics of what a printed circuit board was, the components you find on top of it, and the various things that, you're basically going to find. The second thing we did is we covered some techniques that you can use to reverse engineer it, using like continuity testing and looking up package names and numbers and stuff. And we also showed you how you can do these techniques. You apply these techniques to fix a function generator. So today is bus and interface analysis. A lot of in a lot of electronics, you're going to find that there are components that are connected to each other, and they also need to talk to each other. So we're going to go over some three common protocols that are used. Well, there's probably more than 3 protocols used between hardware devices, but we're going to look at the 3 common ones. I'm going to show you how to identify the interfaces on hardware, and then we're going to go into looking at how to use the SALEAE logic analyzer. So what am I talking about when we're looking at bus versus interface analysis? So I tend to group them into these two categories, where bus analysis is sort of like a passive technique. It's at pin level. You're going to be looking at the signals that are coming out of a chip, and the type of tools you're going to be using in this case is, a logic probe is not really going to tell you anything. All it's going to do is going to tell you, if it's a 1 or a 0, and it'll beep like pretty quickly if it's like oscillating between 0 and 1 pretty fast. Sometimes things are held logic high or logic low, and that's when you'll see the green or red light. And then there's a logic analyzer, which is useful when you have like an address of data or a lot of data coming over more than one pin. Then that's when you want to kind of like use the logic analyzer. And the types of protocols that you would see over a bus interface essentially would be like, UART stuff, I2C or SPI. When I'm talking about like an interface analysis, that goes a little bit more active in some sense. And by active, I'm talking about like using a JTAG emulator or hooking up to the UART terminal of a device. And that's where you would get like serial data coming out, and it puts it in this nice pretty terminal form, and it's human readable sometimes, depending if you have it at the right baud rate. And we'll go a little bit more into detail further down in the presentation on what I mean by that. And the tools you would use in this section would be like a JTAG emulator or a terminal emulator. And this is more system level, because when you're dealing with JTAG, you're going to be talking to more than one device. It depends on how it's set up and stuff like that, but JTAG usually goes between several devices that are JTAG compatible, and usually everything will be sitting on that same chain. So moving on to bus analysis. So what you need to do when you first start bus analysis, you need to be able to identify the peripherals of interest. So like, what are you trying to go after? What are you looking at? you're more than likely are going to be doing or performing bus analysis with components that are attached to the processor, because the processor is the one that talks to all of its peripherals. It tells, you know, the processor decides when it's going to go read from memory, write to memory, or whatever, or the processor decides how it's going to, you know, push data to an FPGA for it to calculate or, you know, perform its functionalities on, or, you know, perform the functionalities that it's supposed to. So then how the processor is communicating with the memory or FPGA or whatever other peripherals are on the board, it needs to speak some sort of common protocol. So we have to identify what protocol it's speaking in order to be able to, you know, sniff the data. So what are, there are two categories or two types of protocols you're going to find, or it's grouped into two different types, serial and parallel. And the most common protocol we have is just, you know, serial communication. And when people say it's using serial, this is the type of serial they're talking about. Serial communication is basically transferring data between, you know, one device to another, one bit at a time. It's also, you can get away with, you know, performing or doing serial communication with a single wire, but never more than 4. And this can be asynchronous or synchronous. When it's asynchronous, you're not going to have asynchronous serial. You're not going to have a clock. There's going to be no clock, and it's just going to be data coming out of one pin, and that's how they're able to get away with performing serial communication over a single wire. It uses less wires, and there's less I/O pins. The only thing is, it's on the developer to ensure that you're transferring data correctly between, you know, point A to point B. So in the beginning, the developer has to say, you know, I'm going to be transferring data at this clock rate, and this is how it's going to look. So what are the rules of serial? Like, well, I mean, these are the rules of serial. This is what defines how data is transferred between point A and point B. There's going to be some data chunks, data bits that are going to be transferred, and then some synchronization bits. How are we going to, you know, sync up our data, and how do I know that this is the beginning and end of data? And then there's a parity bit, basically, that checks to make sure that you are, you know, you get all the data that you're actually sending over. And then there's some sort of clock rate, some sort of clock that's either pre-known or it's actually a wire that is sticking off of, you know, the serial interface. So if you're given a clock, that's awesome. If not, then you will have to sort of start to trial and error. You know, try to figure out at what clock rate is, you know, the device A is sending me, and vice versa. So let's take a look at I think I skipped this. No, I didn't. Nope, okay. So let's take a look at data bits. The data bits are essentially the middle part after you say, after you send like a start bit. It says here, this is a start bit. The data bit, it can range anywhere between 5 to 9 bits that are transferred at a time over serial. You determine how many number of bits you want to transfer per session, per like data block or data session, or I think I'm going to call this a serial frame. So we want to know how many data bytes you're sending per frame depends on you. You have to decide what it's going to be, but usually it's the developer or the person who is programming the serial interface that says, I'm going to be transferring this number of bytes. You're more commonly going to be sending 8 bits at a time. Most often you're going to see 8 bits transferred. And then you also have to decide whether or not you're going to be transferring most significant bit first or least significant bit first. That's all up to you. You defined it. This next thing is synchronization bits. This is the beginning and end of a serial frame, essentially. And the synchronization bits can either be 2 or 3, depending. The only thing that will change the number of bits that you're using is a stop bit. The start bit is only 1 bit. It's always only 1 bit. And then you define whether or not your stop bit is going to be 1 or 2 bits. And most often, more commonly, you're going to find that your stop bit is 1 bit. And that marks the beginning and end of the serial packet. The next thing is the parity bit. What this does basically is it checks for even an odd parity. It counts the number of ones that are transferred, and it says, well, I transferred this many ones and it's going to be even or odd. So it's not really the best error checking mechanism, because if you lose 2 bits of data, then your parity check is no help. So most often this error checking at this level is almost negligent, I guess, not negligent, but negligible, because like it's not going to help you in any way. It's not the best parity checking. It's not the best low-level error checking you can have. Most often it's done at the next level, handled by like your cards or your NIC cards or whatever. But it does check for even an odd parity. You can also just throw the whole bit away and not even care about parity. So it's like no parity. There would be no bit used for it. So the last thing is the baud rate. The baud rate defines at the rate at which bits are transferred. So it's it's measured in bits per second. So when you look at this, when they tell you the various characteristics of a baud rate, you basically say, you have a transmitter, and the baud rate defines how long the transmitter is holding the serial line high or low, and then the receiver on the receiver's end, it's the period at which the data is sampled. Some of the more standard rates you're going to find when dealing with hardware products is like 1200, 2400, 4800, 19, and so on and so on. You're hardly ever going to find something clocking 115K and above. This is probably the highest you'll ever go. But if you notice, looking at these standard rates, there's one rate that's missing, and that is the most common one, is 9600. You're most often going to find like 9600 baud rate used on most electronic devices. And when you're dealing in the world of serial, this is like the most common nomenclature you're going to find: 9600, 8 and 1. What that means is this particular serial interface is operating with this communication protocol characteristics, where it's using a 96,000 baud rate, 8 data bits. It's transferring 8 data bits at a time. There's no parity, and there's 1 stop bit. So when let's take a look at an example. What is this going to look like? Here's an example of what it looks like. So we have a start bit, which in this case, our stop bit is going to be a 0, followed by 8 data bits, followed by no parity, so we're not going to find another bit basically used up. So the number of bits that we're going to see per serial packet will be 8 plus 1 start bit and plus 1 stop bit, and that's going to be 10 bits per serial packet. So going back to our example, our first 4 bits of data is 1, 1, 1, 1, 1. Our second 4 bits are 0, 0, 1, 0, followed by a stop bit, which is going to be 1. So that's our first serial packet. And if the sender or the transmitter says, I'm transferring this stuff in least significant bit first, what are we sending? It evaluates to F. The second one with least significant bit first evaluates to 4. The last one, which is a little off, my slides are a little off here, but The first one, 1101, evaluates to a B, and then the 0101 evaluates to a 4 in least significant bit. So what does that look like when you're looking at hex? You're transferring ASCII characters. It's 0 hex 4F followed by 0 hex 4B, which is O and K. So we're transferring OK in that example. So when you're hooked up to the serial interface, there are times when you may select a mismatch baud rate, and this is kind of what it would look like. A lot of gibberish just coming across. That means you're off your clock, or your clock is not syncing up with the other person's clock. And what you got to do is you got to find a way to receive data at the same clock rate, such that you can get the correct data. So when you get something like this particular output, you want to go back and just start doing trial and error over the various standard rates that I gave you in the beginning. Like under baud rate, I said that the standard baud rates can range between like 1200, 2400, 4800, 19,200, or 9600. There's various other types of standard rates you can try, but almost the more common baud rate is 9600, which is the one we were taking a look at before. So moving on, how does this look in hardware? Well, you have two devices that are going to be both speaking over some pins, and those pins will be set to or assigned to be the receiver and transmitter, and then you'll have some sort of ground. So the reason why you need ground is so that you have some sort of reference of the ground reference, like the voltage level of what you are trying to measure between 0 and whatever voltage it's ranging. So there's going to be some sort of oscillation, and we'll get into further down. You'll see why. Further into the presentation, you'll see why we need ground as a reference. So there are two. So serial data can be transferred in one of three ways. There's a full duplex, where you can send, one person can send and receive, the two devices can send and receive at the same time. Or you have a half duplex, where only one device can send data over a particular bus at a time. So device A would have to send data and then release it, and then device B will send it back, and vice versa. Or there's a simplex. Simplex is where there's only one, data is only going in one direction, where it's going from the device A out to device B. And in that case, it's more like sending data out to LEDs. You don't really care about data coming back, or whether or not the LED is on or off, or if it received your data correctly, or an LCD screen. You just send data out to the screen. So how does this look at the signal level? Well, there are a variety of ways that the serial signal is being accomplished. The more popular hardware implementation is like the TTL or the RS-232, which is probably what you're more commonly aware of. But TTL is more or less used by microcontrollers and integrated circuits. And for TTL, the voltage level is going to range between 0 and 5 volts. So when the voltage goes to 5, it's going to signify a 1, and when the voltage is at 0, which is ground, it's going to signify a 0. And usually the other states that VCC, or 5 volts in this case, is indicated as idle state or the stop bit. So, or a bit level 1, right? And then ground is either bit level 0 or the start bit. So, excuse me. So Oh, and the other thing too is that TTL can operate, the voltage range to operate at TTL is either between 3.3 volts and 5 volts. And you'll see the reason why this is only primarily used between, devices that are very close together, because there's not going to be a whole lot of voltage drop between the time the signal leaves from device A to device B. Now, if you want to go a little bit further along, like further in range between the two devices, you're going to want to use something like this, like RS-232, where the voltage range is anywhere between, 3 to, plus or minus 3 volts to anywhere like plus or minus 25 volts. You're not going to see a whole lot of the higher voltage in hardware, but you're mostly going to find like plus or minus 13 volts. And just like the TTL, the low voltage is going to signify an idle. No, actually it's very vice versa, but it's kind of like opposite. It's flipped on its head, it's flipped on its head. You're going to find that a value low is going to be is going to signify an idle state, or it's going to be a bit value 1, or it's going to be the stop bit. And if it's a high voltage, if your voltage is high, it's going to be either a bit value 0 or the stop bit. So depending on what you're trying to do and how far you need the signal to be carried, you want to be able to use a voltage between 3 and 25. For the longer distances, you're going to be using bigger voltage, because the longer of a distance that the signal needs to be carried, the higher the voltage is recommended. So that's RS-232. And the next is UART. UART is Universal Asynchronous Receiver Transmitter is what it stands for. And UARTs do exist as standalone ICs, but they are more commonly found inside the microcontroller. So you want to check your data sheet. You can have one, none, or many UART interfaces. So so UART is more commonly used when you want to transfer or translate data between parallel and serial forms. And we'll see a picture in a second on what I'm talking about. Yeah, actually probably don't, but let's go to the next slide. So I2C, I'm not going to really cover it in this particular section given time, but I2C uses 2 wires, and the data rate is either at 100K or 400K, depending. You have only one of the 2 options. And then it also transfers 8 data bits at a time plus 1 metabit. And the metabit is essentially essentially helps you determine what type of, like when the next person should start reading. So here's a schematic of what I2C looks like. And you want to use I2C when you have multiple slaves and multiple masters. And what SDA stands for is SDA serial data line, and the SCL is the serial data clock. So you have a clock and you have data. So in the difference between serial data communication, our serial data communication packet, and the serial data communication packet for I2C is that the address, you have an address frame. The address frames indicate the slave. This indicates which slave you want to talk to, and whether or not it's going to be a read or write option, read or write action. And to start the communication, a master will pull the SDA line low and leave the clock high. So if you look at the very, very left side of this picture, you have the SDA line going low and the clock will stay high. And then data is put on the SDA line after the clock goes low. So when on the next falling edge of the clock, that's when data is going to be put on. So, and then the 8 bits of data is going to be put onto the line, and then followed by whether or not it's going to be a read or a write. And then what happens after that is the slave has to pull the SDA line high in order to, is basically an act or acknowledgement that it's now going to read the data off. And then it goes back, the SDA line goes low. It must go low by the 9th clock cycle. And if it doesn't, then it's going to be assuming that the transmission was interrupted in some way. So, and then once it pulls it low, it starts to read data off, and then it signifies an acknowledgement at the very end. And then, of course, the stop condition is defined by it going from 0 to 1, a 0 to 1 transition on the SDA line after a 0 to 1 on the serial data clock. So you'll see way at the very end, it says the stop condition is SDA goes from high to low, followed by a low to high on the clock. So this transmission's done, we're finished. So we kind of went over very briefly about serial communication and direct serial, generic serial communication, and then I2C. Now we're going to take a look at some SPI. SPI is a little bit different. So it's sort of in the middle of serial and I2C. I2C is kind of nice and it's a little bit more complicated, but you can have multiple slaves, multiple masters. But in SPI, you're only going to have one master and maybe possibly a in number of slaves. So SPI is synchronous. I2C is also synchronous. SPI, you have a clock such that everybody's clocking at the same rate, just like I2C. And then you have data. There's 2 data lines in SPI. You have the MOSI and MISO. And MOSI is master out, slave in. That's where data goes from the master to the slave. And then the MISO, MISO, is master in, slave out. That's where the data is going from the slave back to the master. So, and we also have a slave select line, which is the orange, and that determines which slave you're trying to talk to. So we're going to take a look at how you would use or analyze some data, or take a look at some data going over the SPI bus of this TI example. So in this example, we have a microcontroller that is on this big MSP EXP board. And then we have a CC3100, which is basically a Wi-Fi chip, and it's providing Wi-Fi access for this MCU. And what we want to do in this example is basically sniff the WPA key. So what I did was we pulled an example, the getting started with WLAN AP, out of the TI examples, and we configured the CC3100 to be in AP mode. And what this will allow you to do is any station within its range will be able to connect to it. And this particular application or this implementation is using SPI to communicate with the CC3100. So what did we do? Changes we made to the AP settings of the MCU, which is the MSP, I already forgot the model, but the MSP, that multi-controller underneath, is we changed the AP to be called no secrets. We set the password to secrets, and then we selected the security mode to be WPA. So turning it on, let's see, can we see it? Yep, there it is. We can see the no secrets access point. Next, now we're going to try to see if we can sniff the WPA key off of the CC3100. And how we're going to do this is we're going to use the SALEAE logic analyzer. So most logic analyzers are going to come with wires, essentially color-coded wires, and each one of these wires is going to correspond to a pin, essentially. And you'll see how this correlates with some channels inside of the application. But essentially, I numbered these from 0 to 1. So 0 will be this black line, followed by a brown, which is the 1, all the way down to number 7. But if you can see, in my mind, when I first look at this, I always signify, a black line to be ground and a red line to be some sort of voltage. But in this particular case, we're using the gray to signify ground, and you're almost always going to find a ground label on a line of a logic analyzer. So that is where you want to attach that line to the ground of the line, to a ground pin on the board. And what that does is it provides the reference. You remember the reference of, how far voltage is oscillating from, its reference. Essentially, it's the ground voltage. And the black line here is actually a data line. You can hook it up to any pin you want. And that correlates to the channel numbers that are inside of the SALEAE logic application. So you have channel 0, 1, 2, 3, 4. And if you get confused, you can say, well, the color coding is there. So where are we gonna attach these probes to? Well, we gotta look at the CC3100 pinout. And when you take a look at the pinout, and this is inside of a data sheet that we found, we can see that there is UART, and then there's an SPI clock to the left, and then we have our other SPI pins over on the right. You do see an IRQ kind of color-coded to be the same color as the SPI stuff, but usually that's used when you want to, when one of the slaves wants to talk to the master, you would use the IRQ to say, hey, master, I want to talk to you. And then that's how the master would know that there's a slave ready to transmit some data over to the master. So we have SPI chip select, we have SPI MOSI, we have SPI MISO, and SPI clock. That's all we need for now. At the very least, that's all we need to be able to see any type of data. So now we're going to connect the probes. Make sure you attach ground to one of the ground pins on your board, so it provides a reference of 0. And then you attach MISO, MOSI, the chip select, and then we have our brown over connected to the clock. So now, what's really nice about this SALEAE logic analyzer or SALEAE logic application is it comes with some preset analyzers. And if you look over on the right, you click the little button there, and there's going to be a drop-down menu, and it's going to say, well, it supports all these various protocols, and the one we're interested in now is SPI. So we make that selection, select SPI, and then we go over and configure the channels. And then this menu is going to pop up. And what we do is we define which probes are connected to which pins. So our clock is on 0, enable enable in this case is actually the chip select. It's like when a chip is enabled. So it's going to be 1, and then MOSI and MISO at the very, very, very top. We set those up to be channel 2. If you weren't paying attention earlier, I put MISO on 2 and MOSI on 2 and MISO on 3. And then you can also keep the color coding next to you. There's sometimes I can't remember exactly which pins I had it on. So next thing you need to do is determine what mode you're going to be transferring data in. They're the next 1, 2, 3, 5 drop-down menus. How are we going to do this? So there are 4 modes that can be defined. There are 4 modes of SPI transfer, or 4 SPI transfer modes, I'm sorry. And it's either mode 0, mode 1, mode 2, or mode 3. And how you determine those modes are based on the clock polarity and the clock phase. And what do I mean by this? So clock polarity is essentially when data is ready, or when data is going to be available. So when the clock polarity is low, so it's low when it's inactive. So when the clock is low, which is the left side, it's inactive. When the clock goes high, then it's active. So, and then if the clock polarity is 1, it's high when it's inactive. So there's nothing happening when it's low, when the clock is high. The next thing to see is the clock phase. Determines when you want to sample data. So when the clock phase is equal to 0, you're going to be sort of sampling data on the leading edge or the first edge. And then when the clock phase is equal to 1, you're going to be sampling data on the trailing edge, which is the right side of the clock. Now, let's take a look at what mode 0 is going to look like. So mode 0 is when the clock polarity is equal to 0 and the phase is equal to 0. And what that tells us is that it's inactive low, and then we are going to be sampling data on the leading edge. So you can see at the very top, the clock is low. And then when it goes high, we want to sample data on the leading edge. So where you have this green line is where you want to sample data. So then depending on whether or not this is in, you're trying to sample data from MISO, MOSI, you'll see the data that at the point where these two are, at the point of the rising edge, the leading edge is where you want to sample data down below. So 99% of the time you are going to be in this mode. If you have no idea which mode to start in, like when you first come to attaching your probes to an SPI interface, you want to start in this mode, mode 0. And then I hardly ever see mode 3, but this is an example of mode 3 where the clock polarity is inactive when it's high. Clock polarity is 1 and phase is 1. And what that means is that the clock is inactive when it's high and it's active when it's low. And then our phase is going to be on the trailing edge. So since the clock polarity is 1, this kind of looks odd because it almost looks like the mode 0. And it's because of the shift of it. If we were to change the phase to 0, then it would be sampling data on the leading edge, and it would be closer, one clock cycle to the left, or not clock cycle, but one peak to the left, and that would be along this edge here. But it looks really close to what mode 0 is. So you would be, but you've kind of flipped the clock upside down. And then that's where you would be sampling data in this when the phase is equal to 0. But when in doubt, always set it to mode 0 and see what happens. Nine times out of 10, you're probably going to get some sort of data on your in your probe. So the really nice thing about this too is we can hide the rest of the channels because we don't really care about 4, 5, 6, or 7. And then when you don't have a whole lot of stuff connected, it's better because you have more memory to use to capture a lot of your data, or to sample. You can get more samples. So here, what we're going to do is we're going to start it's not start simulation, but when you have everything connected and you have the logic analyzer connected to the board and you have the USB plugged into the machine, you are not going to actually see start simulation up there, and you're not going to see the disconnected next to the SALEAE logic name up the top. You see where it says disconnected? It's actually going to be connected, and that's going to actually say start. So what we're going to do is we'll click start, and then you're going to be waiting. You're waiting for a trigger. In mode 0, what you're waiting for is, or actually, I set the trigger to be, which I'm going to go on the next slide. We're waiting. We started to capture. I told my logic analyzer to trigger on a falling edge of the chip select. And the reason why I chose that is that there's going to be a lot of data that's going to be going over the SPI bus. It could be data going, to other chips, because those lines are all connected to each other. So there's probably only one SPI interface coming off of your microcontroller, and it's going to be going out to several slaves. So your microcontroller can be talking to other slaves, but I really don't care about those other slaves. All I care about is the CC3100. And so I connected my black channel to the chip select of the CC3100. So I want to know when that chip gets selected. Then I want to start sampling data. So now that's my trigger, and I'm waiting for it. Now what do? I turn on the TI chip, and then you're going to see something called sample. And then you're going to see something like this where it's sampling data, and it'll sample as much data as it can, but that's dependent on how much information or how much space you have on your laptop or your computer or whatever. So now you see this. Now I was in this particular example, I was sampling at 24 megahertz, and you can see that it doesn't look very uniform. If you take a look at it, it's like the data on the master out, slave in. I'm most interested in that because there's some data that's coming from the master to the slave. My master is the microcontroller, my slave is the CC3100, and what my microcontroller doing is configuring the AP, and somewhere along the way it's transferring the key. And so when we take a close look at this, my clock isn't necessarily uniform. There's some gaps in the, the third one. There's like a gap in between it, so the clock is staying high for a tiny period of time, and then it goes back down low. When I see something like this, it kind of calls out to me that, hey, I'm not getting all the data that I need. Plus, my data that's coming off of the MOSI is, stretching out beyond the clock signal. Usually what I'll see is like data, and then the clock is uniform all the way across, and then it drops off, and then it comes back, and then it drops down to 0 and then comes back. But you should see some data, some clock signal all the way across. So if we zoom in on this, what we'll see is, my clock, it's crossing the boundary of the data line. So I'm like, well, I shouldn't be getting that data. I shouldn't be seeing that. But you also see, if I did a measurement of this clock, and it told me that the clock frequency was about 12 megahertz, and where I see that is over in the measurements on the right-hand side. You see width, period, frequency, and then where I put my markers. But it's about 12 megahertz. So what might be wrong with this? So what might be wrong is that my sampling rate is too low. Typically what you want to do is you want to sample at like at the Nyquist rate, which is 2 times the highest frequency. And in this particular example, my target's frequency was set to 12. We'll look at it on the next slide, but let me just go back to the information, the thoughts about sampling. So the maximum sampling rate for this particular SALEAE logic analyzer is actually 24 megahertz. And if I did that drop-down menu, that's the highest it'll go. So I was like, well, what's wrong with this? I need to take a look at the data sheets for the CC3100 and the MSP430. That's what it was, MSP430. And we'll see what the clock rates look like. Because when you do, when you sample anything, you do need to be at least 2 times the highest frequency. And something, so you always have to sample at something equal to or greater than the Nyquist rate. So the TI clock rates. So we have the SPI peripherals is clocked at 25 megahertz. That's what I found in the code. This is all written in the code. And the CC3100 is basically using 25 megahertz divided by some divisor. And the divisor was set to equal to 2. So, and that basically gives me about, 12.5-ish megahertz, which is what we were seeing in the previous example. When I sampled at 24 megahertz, it was showing me a clock rate of 12 megahertz. So that was a little bit too fast for my particular logic analyzer. So, well, to show you the differences, I was like, well, let's change that to 5. So if you take 25 megahertz divided by 5, by this division, we're going to get something clocking at around 5 megahertz for the CC3100. So now let's go back and try to sample again. The SPI clock is at 5 megahertz. Now we're sampling at 24 megahertz. That's definitely much greater than the Nyquist rate, much faster than the Nyquist rate anyway. So now we take a look at our data. It looks much better, looks much more promising, because I see that my clock signal is actually, right over my data. I'm sampling data at the right time, and there's some gaps in between it. It looks much nicer. I'm starting to see stuff that makes sense in some way. So if we look closer, how do we see this? Remembering that we are in mode 0, we told the logic analyzer to capture data in mode 0. So mode 0 is the clock is low. When the clock is low, it's inactive, and we're sampling at the leading edge. So our clock, when it goes low, and we need to sample at the leading edge. So the very leading edge is the very first peak. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. 8, which goes back to the thing that said that we were going to be transferring 8 bits of data per transfer. So I'm looking at the data going out of the MCU, which is the MOSI, to the CC3100. We see that all on this next line. So when we take a closer look, sampling on the leading edge, we have a 0. We sample here on the next leading edge with 1, 0, 0, 1, 0, 0. 1, 1, 1, 0. And then we said, okay, well, what did we specify it to capture at? I can't remember what I set it to. Probably most significant bit first. So the very first one is going to be a 0, 4, 0, 0, which is going to be a 4, and then the next one's going to be 8, 4, to 0, which equals 14, and that transfers into an E. So then this in hex form is going to be 0x4E, which is in ASCII, that is in. So you can also go back and tell, let me go back, I'm sorry, go back. If you see in the little red section, you see the letter N, is because I told the logic analyzer to display my data in ASCII. Now you can also change it to say display in hexadecimal. So if you change it to say view in hexadecimal, you're going to see the output in hex, which is 0x4E. Now, there's also an option to export the data to a text file, and what that's exporting is everything that's inside of the logic analyzer. So like the time it will sample that, and what the value of each line was at that particular time. So this was a little easier because I basically wanted to hurry up and find whether or not I actually can see something, so I know what I'm looking for. And not a lot of cases, this isn't true. You can't just go and open a text file and start searching for ASCII characters. But I knew that it started with an N, my password anyway, or my access point started with an N. So I open this up into a text file, search for the letter N, and I see the letter N there. So if we make it a little bit nicer and pretty, I tabbed it over a bit, and you can see it says NOSECRET plus the S, no secrets. So that's my access point name. So then you can also, now that that looks much better, and we can also see this in the logic analyzer, you can start to see the data in and 0 followed by the 0, and like, ooh. So I wasn't able to, I mean, you can scroll and scroll and scroll. You're going to have a lot of data, so you can take this waveform and scroll to the left, scroll to the right forever, and try to find where this thing is at. But I opened it up in text file, verified it was there, and now I'm back here looking to see it, and I was like, well, can I actually see the AP name? And there it is. And you can see that this particular chip select went low, and a lot of data was transferred, which was this no secrets AP name, and then it went back high for this transfer. So I tried to see if I could sample it at 16 megahertz because we were, what was 25 divided by 5 was about 5 megahertz. So if we go to a lower frequency, we can still see it. I still found the AP name, and then I look further down, and I found the WPA key. And this is the WPA key, S3CRE, not E, but 3T5 bang. So I just wanted to see how close we could get to the 10 megahertz, or I'm sorry, how close we could get to the 5 megahertz sampling rate. So this logic analyzer can do 10 megahertz, I believe. I can't remember right off the top of my head, but I think the lowest I tried sampling at was 16 megahertz. And I was still able to grab the information. So sniffing TI at 12 megahertz. Oh, sorry. Sniffing the key when it was at 12 megahertz, when the TI chip was set at 12 megahertz, and the clock wasn't shifted. The clock was shifted and it wasn't consistent, and you could see that some of the data wasn't right underneath the clock, which was kind of an indicator. It wasn't a pretty graph anyway. It wasn't nice, and you couldn't see. There were some things that were missing. Clock wasn't uniform above the data and stuff like that. Another thing that can happen is users can attach the probe to the wrong clock. And that's kind of what I did. I was like, let's try this on the wireless DSL router that we showed you in the last session. Let's take a look and see if we can read off some data. So I attached a probe to it. I connected some stuff, and I did not connect it correctly. So when you look at this, you're like, wait, that doesn't look like a clock. What's wrong with this? So then you have to go back to your board and take a look and say, well, that's not correct. because I looked up the data sheet for this and I have it switched. I have the, I actually have the, sorry, oops, sorry, go back up. I have the, it looks like I have the MISO on the clock, and the clock is not even attached. So then I had to go back and attach the clock to the right pin and then try it again and sample at 24 megahertz. And I'm starting to see the same sort of problem I saw when I first hooked this up to the TI chip, when it was, when the SPI clock was like clocking around 12 megahertz. You see the clock is going over the data sections, and then there's a lot of gaps in the clock up there. There's like more black, you know, wider waveforms in some sections. And that kind of tells me that I'm probably not clocking fast enough to collect data correctly. So I need a better logic analyzer. So one of two things you can do. Do what I did, go back into the code and modify it, or buy a better logic analyzer. So, so when I took a look at this particular SPI flash chip, which is a Micronix flash chip on the wireless DSL router, the data sheet specified that the serial clock could be set up to 80 megahertz. And so if it's actually set to 80 megahertz, then I am not clocking at the correct sampling rate that I need to clock at. I need to be at like 160 megahertz. And there are some newer SALEAE logic analyzers that are out there where they can clock at 500 megahertz or something like that. They're a little bit more expensive, and we don't necessarily have that here today, but it is possible to sample at the rate you need to. Next thing we're going to go over, and it's just a really quick brief overview. There's a lot that needs to happen here, but not enough time to talk about it. So active analysis, this is where you want to do some, like, you know, debugging or firmware extraction, or you want to you know, be able to pull some of the code that it's running off of the board. And how you do this is through some tools like JTAG or over the UART, over a serial terminal. But very quickly, we're going to talk about JTAG. It's a really simple overview. JTAG is basically 1, 2, 3, 4 lines is all you really need to be able to tap into the JTAG on a device. And the very first one is test mode select, test clock, TDI, which is test data in, and TDO is test data out. Here I marked it, I forgot. But you can get away with just the clock and data in and data out. And then there's also two that are not here, which is like ground for reference. You need a ground to be able to tell, you know, how far from ground your voltage is varying, to be able to tell you whether or not it's a 1 or a 0 being transferred. And then you have the test reset, software reset lines. Usually you don't really care about that stuff. All you really care about is the clock and TDI, TD out. And then next thing you know here, next thing is the JTAG headers. Where are you going to find them on the board? Usually you'll find them like without pin headers in it, or there'll be pin headers in it, and then you can attach your probe or your cable with the connector on it. And sometimes what you have to do, if you don't know where it's at, you have to kind of like probe it out, like we did with continuity testing in the very beginning. So what you have to do is you'll have to go and check the check where the JTAG pinouts are coming from your device, and then, you know, correlate that to one of those headers. And these are the more common pinouts for, you know, ARM stuff. And if you look over on the right, there's the TI MSP 430. So these headers are actually sitting on your PCB board somewhere on the board, and then you are going to you're going to find out where these JTAG pins are coming out of your multi-controller, and then you're going to sort of like do the continuity testing and beeping out, trying to find where it is on the board and what header it's going to. Once you find that, then it's pretty easy to just hook up to it, and then, but you also need a JTAG emulator, which then can, you know, speak the language it needs to speak. A couple of examples. We have a fly swatter here, and that's the one up on the left. It's a very simple one. It uses, I can't remember the, OpenOCD, right? OpenOCD is what it uses. And then we have the J-Link, that's more or less used for Windows type stuff, and I mean, it has a Windows application. And then we have the BDI 3000, which is a more expensive version, but I've actually used J-Link. It's pretty straightforward. Once you have the configuration file set up for each one of these type of emulators, you have to define, you know, if there's a chain, how many bits are in the IR register. It's a very in-depth thing, but once you get it up and running, you have it connected, it's, you know, the world is your oyster, essentially. You can determine, or you can stop, you can start and stop the microcontroller, you can, or the microprocessor, sorry, and you can, you know, read what's on a particular address line, or you can tap into the particular part of memory that was mapped in from a RAM, or you can also like say, okay, well, I want to copy this that was copied out of RAM. It's pretty nice. The other thing you can run into is where there's multiple devices on the JTAG chain, and this is what they call daisy chaining. And what happens is the TD out of device A is put into TDI of the next, and so on and so on. Device 2 TD out is into TDI of device C of 3. And then what happens is data is pushed through all those devices and finally comes out at the very end. There is a way that the emulator can put, you know, particular devices in bypass mode so that you're only getting the data that, or getting the data that's being affected for one device. So you can just have the data come in in one device. So if you put a 1 and you say device 1 and device 3 are in bypass mode, there is a way to do that, such that the data that's coming in on TDI goes straight through unaffected to TDI of device 2. And then it comes out unaffected of, there's nothing that's going to happen over device 3, and it'll just come out of TDO so that you can see it here. Sometimes there's instances where you can't put those devices in bypass mode, and at that time you're going to start to do some more evasive things where you actually stick 2 wires into those between device 1 and device 2, and then stick another wire to get the data off of TD out between device 2 and device 3. I mean, it's possible, but then you're getting into a more invasive approach at that point. Some of the configuration that you need to define for emulators are like number of devices on the chain, if any. It could be 1 or many or more. The adapter speed, how fast you need to start reading data off, and the register length, the endianness, just like everything else. And then debug servers. If you want to, some of these emulators will come with debug servers, and then you just have to define, you know, the socket and the address it's going to be listening on so that you can connect to it. And in conclusion, there's a lot of stuff that you can do, a lot of bus analysis and signal analysis you can do between devices, so long as you know what you're tapping into. And any of the serial communication protocols that we're talking about, you can see those and you can sniff it. You just have to be clocking at the right level, right sampling rate and whatnot. As far as the more active approach, when I'm talking about like JTAG and like the terminal emulators, that's more of a high level. That's more high level at a system level. You start to see the interactions between like the main device, which is the microprocessor, and its peripherals. So you basically can do a lot of analysis. I mean, there's many things you can do with a lot of this stuff. So if you want to learn more, you want to see how to use the logic analyzer for like I2C or regular serial or any of the other ones, I2C and stuff like that, or try to figure out how to attach this to something that's clocking at a higher rate than your logic analyzer, we can probably help you, or come to the paid version and we'll discuss it a little more. But thanks. Hope there's no questions. I'm just joking.